Okay, I've got the two parts of the fundamental theorem of calculus written on the board here. I've used the version here where I write the integrand as f prime rather than just writing a little f and then saying that big F is an antiderivative. That just makes it a little bit easier, I think, to see the connection between things. Okay, but I want to just take a moment and kind of look at the big picture here, because these are really just two sides of the same coin. It's a really powerful concept. Notice here I started with a function, little f. I took an integral of that. Then I took a derivative. Notice what I got, little f. Now, something did change. I started with this as a function of t, and then because the area function that I defined using this integral was a function of x, when I took the derivative, of course, I got a function of x. But essentially, I started with something. I took an integral, I took a derivative, and pretty much back to the function that I started with that one important change. Now notice what's happening here. I've got a function big F, I've taken its derivative. Now I'm going to integrate. What do I get? I get big F back. Now again, the form in which I get it has changed. I don't get big F just the function. I'm getting it evaluated at these endpoints and subtracting. So I'm no longer getting a function. I'm getting a number that I've calculated with that. But, modulo these details, basically I took a derivative, I took an integral, I got my function back. I took an integral, I took a derivative, I got my function back. We've seen that before. With numbers, if you plug a number into a function, and then you plug into another function, and you get that number back, and that happens in both directions, we call those inverse functions. And inverse functions undo each other. So what the fundamental theorem of calculus is saying is that differentiation and integration are inverse processes. They undo each other. And that's really amazing, because we started, if we look at the geometric questions that we were asking, what's the slope of a line? What's the area or the signed area between this curve and the x-axis? Didn't seem like there was a strong connection between them. We start to see the connection a little bit more when we think about what these things mean. A derivative is a rate of change, and metaphorically, the signed area that we're calculating in our definite integrals is an amount of change. It's the amount of change in f. And certainly the amount of change and the rate of change are going to be related to each other. And this basically says those two seemingly very different things that we were doing, calculating slopes of lines and calculating areas, are actually inverse processes because they are all dealing with change. One is dealing with the rate of change, one is dealing with amount of change. They're very, very related. So that's the gist of the fundamental theorem of calculus, that integration and differentiation are inverse processes. And that's why we use the indefinite integral sign for finding a general antiderivative, because we're saying let's do the opposite, let's do the inverse of taking a derivative. So there really was a reason that we used that symbol back in chapter 4. I know the book didn't introduce it at that point, but that's what's going on. These are inverse processes that undo each other.